Welcome to Reinforcement Learning Revisited, for those who've seen it before. In this short video, we'll walk through key reinforcement learning concepts, policies, values, the Bellman Equation, and how they fit together, all through visual intuition. If you've seen RL before but want a clear, structured refresher, you're in the right place. Let's begin. Let's start with the idea of a deterministic policy. This means that for every state, we select exactly one action. In the diagram, each node represents a state, and the edges show the transition probabilities when a particular action is chosen. The thicker the edge, the higher the probability of that transition. Here's a quick example. In the current policy, action A is selected for state S1, shown as an orange circle. Taking action A can lead us to either S2 or S3, each with a 50% chance. In another example, we consider state S4, again marked with an orange circle. The selected action is B, which can transition to S5, S7, or S8. These have probabilities of 0.5, 0.3, and 0.2 respectively. Now, let's talk about state value, denoted V. This represents the expected return, the sum of future rewards from a state. Each state under a policy has a value, indicating how desirable it is to start from that state. The thicker or bolder the node, the higher its value. You might also wonder about the arrows. They're reversed here to show the flow of value. Let's look at the Bellman equation. Suppose we take a deterministic action A in state S1. Then the value of S1, V1, is the weighted sum of the values of the possible next states plus their immediate rewards. In this case, V1 equals the probability of transitioning to S2 times the sum of R12 and V2, plus the probability of transitioning to S3 times the sum of R13 and V3. This shows how the value of a state depends on the values of its neighbors and the immediate rewards. Here's an example to visualize it. Suppose V1 is calculated as 1 plus 2, equaling 3. The probabilities of transitioning to S2 and S3 are both 0.5, and the rewards R12 and R13 are -2. If V2 is 4 and V3 is 6, then the flow of value is clear. Half of the adjusted value from each neighbor contributes to V1. The reversed edges in the diagram represent this value flow. In another scenario, the chosen action in S4 leads to S5, S7, or S8. These resulting states all have high values. Based on their probabilities and rewards, they each send value back to S4, 10, 6, and 2. The total value defines the desirability of S4. Let's consider policy improvement. The value of S1 is quite low. It's the lightest green node. This suggests that the currently chosen action might be sending S1 to states with poor outcomes. If we try a different action, we might gain more value. So, let's explore our options. Right now, the policy chooses action A for S1, which gives us a value of 3. But we have alternatives. Action B would lead to S5 or S7, while action C would go to S10 or S11. What values could we gain from those actions instead? Let's break it down. Action B would give us a total value of 11, 5 plus 6. Action C gives us 8, 4 plus 4. Both improve upon our current value of 3, but action B performs best. So the improved policy would now select B instead of A in S1. By choosing action B, V1 jumps to 11. As a result, the value flowing from S1 to its neighboring nodes increases. That increased flow impacts downstream nodes. Now S2 and S12 receive more input, 5 units of value each. But their current values don't reflect this. For example, S2 had a reserved value of 4, but it now receives 7. So we should update V2 to 7. Likewise, S12 should also be updated from 3 to 7. With V2 and V12 both updated to 7, S2 now sends more value to S3 and S12. This value propagation continues. Now, S3 and S12 each receive even more value, 4 and 3, respectively. But their existing values no longer satisfy the Bellman equation. S3 is currently set at 6, but now receives 7. S12 receives 8. We update V3 to 7 and V12 to 8. After these updates, both V3 and V12 reflect the correct values. This whole process of value updates continues iteratively until every node and edge satisfies the Bellman equation. As this happens, node and edge colors grow bolder. One change can ripple through the entire network. That's value propagation. And this is what we call policy evaluation. Policy evaluation is the process of updating state values based on the current policy. Starting from initial estimates, we adjust values through repeated updates, similar to a random walk, until they stabilize and satisfy the Bellman equation. So what is the goal of reinforcement learning? It's to find a policy, an action for each state, that maximizes the expected return. Given an initial state, which actions should we take to collect the most value? Here's the framework. Start with an initial policy. Evaluate that policy by estimating values. Use those values to improve the policy. Then, re-evaluate the new policy and continue the process. In our graph, that means changing some actions, updating value flows and colors, and repeating until all nodes reach their optimal states. This is called policy iteration. First, improve the policy. For each state, examine possible actions and choose the best one. Then, evaluate the policy. Update and propagate values until they converge. Repeat this loop iteratively until the optimal policy emerges. Let's revisit our example. Suppose all states already follow the optimal policy except for S1, S2, and S12, which have lower values. We focus on these three. We evaluate new actions, update their values, and improve the policy. The policy changes. Now, new actions are selected for S1, S2, and S12. Next, we move into policy evaluation, updating the values based on the new actions. After one round of improvement and one round of evaluation, the graph updates. But we're not done. We continue iterating this process until the optimal policy is reached. Now we switch to value iteration. It's similar, but instead of fully evaluating the policy in each loop, we only update values once and move on. This is an incomplete policy evaluation. It speeds up convergence, even if intermediate values don't fully satisfy the Bellman equation. So here's the difference. Policy improvement still works the same way, but evaluation is quicker. Just one pass, and then back to improvement. For instance, suppose we update V1, V2, and V12 as before, but we stop there. We don't propagate the updates further. V3 remains unchanged for now. We proceed to the next round of policy improvement. This faster loop drives value iteration. That wraps up our tutorial on reinforcement learning. I hope this helped clarify key concepts. Thanks for watching. Until next time.